What if I told you that a building technique from 2,000 years ago could outlast anything we build today? That ancient people stayed comfortable in 120-degree heat without spending a single dollar on electricity? That one person, using nothing but rope and wood, could lift what would take 60 modern workers? You'd probably think, sure, but it was primitive, slow, inefficient. But here's the thing, what if we got that backwards? What if ancient technology wasn't just good for its time, what if it was actually better? Today we're looking at 9 technologies that challenge everything we think about progress. And the question isn't how did they survive without modern tech? The real question is, what did they understand that we've completely forgotten? Egyptian bellows-enhanced hearths. Forcing the fire. For our last system, let's go to ancient Egypt and focus not on a structure, but on a tool that completely changed our relationship with fire: the bellows. This might sound simple, but adding bellows to a fire is a quantum leap in heating tech. It's the ancient ancestor of the forced air furnaces we use today. A fire needs fuel, heat, and oxygen. For thousands of years, people were pretty passive about that last part, just relying on natural airflow. This meant fires were often smoky and didn't burn very efficiently. The invention of the bellows, as early as 1500 BC in Egypt, changed everything. A bellows is just a primitive air pump, a bag with handles and a nozzle that you squeeze to shoot out a jet of air. When you aim that jet of air at the base of a fire, you dramatically increase the oxygen supply. The result? A fire that burns hotter, cleaner, and with way more efficiency. It's like adding a turbocharger to your hearth. This was a game changer. For metalworkers, it meant they could finally get fires hot enough to smelt metals. But for heating, it meant you could get way more warmth out of the same amount of fuel. A fire fanned by bellows could heat up a room quickly and powerfully. It also burned fuel more completely, which meant less smoke inside the home. That core principle, using forced air to improve combustion, is the bedrock of modern heating. Every gas furnace today has a fan that pushes air through the system. The ancient Egyptians, using simple leather and wood bellows, were harnessing that exact same idea 3,500 years ago. This was about manipulating the very chemistry of fire, representing a deeper understanding of how to generate and control heat. The Roman Hippocaust, the dawn of central heating. Let's kick things off in the heart of the ancient world's greatest empire, Rome. When you think of Roman engineering, you probably picture aqueducts and the Colosseum. But one of their most luxurious and clever inventions was hidden completely out of sight, right under their feet. It was called the hypocaust. The name comes from ancient Greek words meaning under and burnt, and that's a perfect description. It was a system of fire from below. The Romans perfected this around the 1st century BCE, and it became the ultimate status symbol, used to heat the massive public baths and fancy villas across the empire. So how did this thing actually work? First, Roman builders would raise a room's floor up on short, sturdy pillars called pilae, creating a hollow space underneath. Outside the building, or in a basement, was a massive furnace called the prefurnium. Slaves would feed this furnace with wood day and night to keep a huge fire roaring. The real genius was what they did with all that heat. Instead of just letting smoke and hot air drift away, they channeled it into that hollow space under the floor. The hot gas would swirl around the pillars, heating the layers of tile and concrete above to the perfect temperature. Imagine walking barefoot on a warm stone floor during a nasty winter in Britain or Germany. That was the kind of luxury the hypocaust delivered. But they didn't stop there. For rooms that needed to be extra toasty, like the hot room in a bathhouse, they designed hollow tiles called tubuli to act as flues inside the walls. The hot air from under the floor would get drawn up through these wall flues, heating the walls themselves before finally escaping through a chimney. This created a room that was warmed from all sides, wrapping you in a blanket of radiant heat. Frankly, it's a more comfortable and bone-deep warmth than what you get from modern radiators, which mostly just heat the air. Of course, this level of comfort came at a price. Running a hippocus took a ton of labour and burned through mountains of firewood, so only the super rich could afford it. When the Roman Empire fell, this incredible technology was pretty much lost to the Western world for 1,000 years. A brilliant idea buried in the dust of history. The Korean ondol, radiant heat for the people. While the Romans were heating the villas of their one-percenters, a totally different and arguably more clever system of underfloor heating was being perfected on the other side of the world. In Korea, they developed the ondol, a system so efficient and central to the culture that it has been used continuously for over 2,000 years. Ondol literally means warm stone, and that's the heart of its design. Unlike the Roman hippocaust, which needed its own dedicated furnace, the ondol was a masterpiece of recycling. It brilliantly integrated the heat from everyday cooking right into the home's heating system. The fireplace, or agunji, was usually in the kitchen, which was built slightly lower than the main rooms. When you lit a fire to cook dinner, the smoke and hot air didn't just go up a chimney. Instead, a network of horizontal stone flues channeled that hot exhaust under the floor of the next room. The floor itself was made of thick, flat stones called gudoljang, which were then covered with clay and oiled paper to make them smooth and waterproof. As the hot gas passed through the flues, those gudoljang stones would soak up a massive amount of heat, basically turning the entire floor into a giant, slow-release thermal battery. The heat would then radiate upwards, gently and evenly, warming the room for hours. Even after the cooking fire was out, the warm stone floor would continue to radiate heat long into the night. Some exceptionally well-designed ondol systems were famous for how long they could hold their warmth. This technology literally shaped Korean life. Because the floor was the warmest part of the house, daily life, eating, sleeping, hanging out, all happened on the floor. It was even considered healthy. There's a record from the Joseon dynasty where King Sejong tells a sick courtier to go rest on a warm ondol floor to recover. The hypocaust was a symbol of imperial luxury that faded away, but the ondol was a practical, democratic heating system for everyone. Its principles are so solid that modern Korean apartments still use a form of ondol, just with hot water pipes instead of smoke. The Chinese Kang bed stove, the ultimate survival combo. Now let's travel from Korea to the frigid plains of northern China, where we find another amazing piece of thermal engineering born from the brutal need to survive the cold. Meet the Kang, or the heated bed stove. It's not just a heater, and it's not just furniture. It's basically the original heated couch, bed, and living room all rolled into one hyper-efficient platform. For thousands of years, families in China's northern regions have relied on the Kang, which has a history going back at least 2,500 years. The basic setup is a raised, hollow platform made of brick or adobe clay that often takes up a big chunk of the main room. Like the ondol, the Kang is a masterclass in recycling heat. A nearby cooking stove is connected to the Kang's hollow interior by a series of flues. The hot smoke from cooking dinner, which would normally just be wasted, is routed through winding channels inside the platform before it finally goes out a chimney. This process transfers the heat from the smoke into the dense brick or clay of the Kang. The key here is thermal mass. The heavy materials absorb heat slowly and evenly. It might take a couple of hours to really warm up, but once it's hot, the Kang radiates a gentle, steady warmth all night long, well after the fire has died. This meant a family could cook their evening meal and preheat their bed for the entire night with the exact same fuel. That's a level of efficiency our modern, single-use appliances can't touch. Life revolved around the Kang. During the day, it was a warm place to work, eat and socialise. At night, the whole family would sleep on it, sharing its communal warmth. Modern studies have even shown that a well-designed kang can cut the amount of firewood needed for heating by over 35%. In a place where fuel was precious, that efficiency wasn't a luxury, it was the key to survival. So we've just seen how 3 different ancient cultures developed incredible, radiant heat solutions that give our modern tech a run for its money. If you're finding this forgotten wisdom as fascinating as I am, do me a favour and hit that like button. It really helps the channel and tells me you want more deep dives into the genius of ancient tech. So ancient people cracked heating systems that lasted centuries, used waste heat from cooking, stored warmth for days. But wait, what about the opposite extreme? Picture this. You're in the Persian desert. It's 120 degrees outside, no electricity, no refrigeration, no AC. How do you not just survive but actually stay comfortable? The answer ancient engineers came up with seems impossible, but it's pure physics. Wind catchers. Engineering the wind. Our journey kicks off in the heart of the ancient Persian Empire, in cities like Yazd, Iran. Look up, and you'll see a forest of strange, elegant towers rising from the rooftops. These are the Baghdad, or wind catchers, and they are one of the most visually striking and seriously ingenious cooling systems ever devised. For centuries, these things have provided silent, totally passive air conditioning to homes and mosques, a testament to an incredible understanding of natural airflow. The problem they had to solve was huge. How do you make life not just survivable, but comfortable, in a desert with blistering temperatures and dusty air? The answer wasn't to fight the wind, but to harness it. A wind catcher is basically a tall, chimney-like tower on the roof with openings facing the wind. As the breeze blows, it's caught and funneled down a shaft into the living spaces below, creating a constant, gentle flow of air that can dramatically drop the indoor temperature. But the genius of the Persian wind catcher goes even deeper. In some of the most sophisticated designs, it works in tandem with another ancient marvel, the Qarnet. Qarnets are vast underground aqueducts, tunnels that carry cool water for miles. Some wind catchers were built directly over these systems. As the hot, dry desert air gets funneled down the tower, it passes over the cool water. This triggers powerful evaporative cooling. The air dumps its heat into the water, becoming significantly cooler and a little more humid before it even enters the home. The result is a refreshing, naturally conditioned breeze, all without a single moving part. In some designs, the tower even acts as a solar chimney. The side of the tower facing away from the wind heats up in the sun. This warms the air inside that part of the shaft, causing it to rise and exit, creating a pressure difference that actively pulls cooler air down into the building. It creates its own ventilation, even on still days. The rediscovery of this tech is profoundly relevant. As cities grapple with insane temperatures and strained power grids, architects are looking to the wind catcher for inspiration. Modern versions are being built into new buildings, like the prominent wind tower in the UAE's Masdar city, proving that ancient principles can anchor the cities of the future. The materials might be modern concrete and steel, but the core principle is identical to the one perfected thousands of years ago, engineering the wind itself. Thermal mass, the power of thick walls. From harnessing the air, we now turn to harnessing the power of the earth itself. Across totally different cultures, separated by thousands of miles and years, ancient builders came to the same elegant conclusion for brutal climates. Build thick. From the adobe pueblos of the American Southwest to the earliest mud brick homes of Mesopotamia, the principle of thermal mass was a cornerstone of comfort. The concept is deceptively simple, but incredibly effective. In a hot, dry climate, the biggest challenge is the wild temperature swing between day and night. A modern, lightweight house heats up fast, becoming an oven during the day, and cools down just as fast, turning into a fridge at night. Ancient builders understood this, and they used materials with high thermal mass like adobe, rammed earth, and thick stone to act as a climatic battery. Here's how it works. During the scorching day, the thick, dense walls soak up the sun's heat incredibly slowly. It takes hours for that heat energy to travel to the inner surface. By the time it finally starts to radiate into the home, the sun has set and the outside air is getting cool. The building then slowly releases that stored heat through the night, keeping the inside stable and comfortable. The next morning, the walls are cool again, ready to start the cycle. It's a remarkable thermal flywheel effect that smooths out the daily temperature extremes. The Pueblo peoples of the American Southwest were masters of this. They built their iconic dwellings from adobe bricks, sun-dried earth, water and straw. These thick walls weren't providing insulation in the way we think of it today. Their magic was in absorbing and slowly releasing heat, not just blocking it. They combined this with smart design, clustering buildings together and building under south-facing cliffs for natural shade during the high summer sun. Today, as we look for more energy-efficient designs, the wisdom of thermal mass is having a huge renaissance. Architects are rediscovering materials like rammed earth, not just because they're sustainable, but for their superior thermal performance. Modern homes are explicitly using massive stone and earth walls to regulate temperature passively, proving that sometimes the most advanced technology is the earth right under our feet. The art of shade. Ancient builders understood a fundamental truth that modern city planners seem to have forgotten. The easiest way to deal with the sun is to simply get out of its way. Before anyone dreamed of mechanical cooling, the most sophisticated climate control system was shade. And nowhere was this art more masterfully executed than in the dense maze-like cities of the Middle East, North Africa, and the Mediterranean. The design of these old cities was a brilliant and deliberate response to a scorching environment. Instead of the wide, sun-blasted avenues we build today, they were defined by a web of narrow, winding streets. This wasn't random. It was a strategy that evolved over centuries. The tall buildings on either side cast deep shadows for most of the day, keeping the ground and the walls cool. Walking through these shaded canyons was dramatically more comfortable, creating a cooler microclimate for the whole city. At the heart of the home itself was another genius shading device, the central courtyard. In traditional Islamic and Mediterranean architecture, houses looked inward, organized around a private, open-air courtyard. This space was the lungs of the house. During the day, the surrounding rooms stayed in deep shade. Fountains or pools were often placed in the center, and as hot air drifted in, it would be cooled by both the shade and the evaporating water. The courtyard also drove natural ventilation. As the sun heated the air in the courtyard, it would rise, pulling cooler air from the shaded rooms and streets into the house to replace it. At night, the process would reverse. The open courtyard would radiate heat out to the clear night sky, becoming a pocket of cool air that would then spill into the surrounding rooms. It turned the whole house into a self-regulating, breathing organism. The lessons here are profound. While you can cool a single building with technology, cooling a whole city requires smart urban design. The ancient model of compact shaded cities offers a powerful alternative to the heat island effect that plagues so many of our modern towns. Okay, so they mastered climate without power. Impressive. But here's what really doesn't make sense. Pausa dramatica. How is it that the Pantheon Dome in Rome, built in 1206 AD, is still the largest unreinforced concrete dome in the world? How is that even possible? We have better materials, better tools, better engineering knowledge, right? Beat. Unless we don't. Unless they knew something about materials and force that we've somehow unlearned. The brute force multiplier. The starting point for our journey is, inevitably, the challenge of moving impossible weights. The focus is on the Greco-Roman crane, a testament to pure mechanical genius. Forget the simple image of men dragging blocks up ramps. The Greeks and Romans developed lifting technology so effective that it revolutionized what a society could build. The secret was their mastery of multiplying kinetic energy through elegant systems of pulleys and treadwheels. The first evidence pops up in ancient Greece around the late 6th century BC, where distinctive cuttings on temple stone blocks show they were being gripped and lifted. This wasn't just an improvement, it was a complete change in the philosophy of construction, born not from a desire for convenience, but from pure, relentless necessity. But it was the Romans who perfected this technology. Engineers like Vitruvius left us detailed accounts. Their simplest crane, the Trispastos, gave one man a 3-to-1 mechanical advantage, allowing him to lift around 150 kilograms, 330 pounds, with ease. One individual, with the right application of physics, could do the work of 3. That right there is a game changer. And they scaled it up. The colossal polis pastos, when fitted with a large treadwheel for men to walk inside, could lift a staggering 6,000 kilograms, that's over 13,000 pounds. To put that in perspective, the Egyptian method of dragging a 2.5-ton block was estimated to take 50 men. The Roman polis pastos was about 60 times more efficient per person. This wasn't just about moving heavy objects, it was about the intelligent multiplication of human energy, a secret that allowed an empire to be built from stone. But here's what makes this even more remarkable. These weren't crude contraptions. Archaeological evidence shows Romans used sophisticated bronze bearings, precision-cut wooden gears, and mathematically calculated rope ratios. They understood load distribution, stress points, and mechanical advantage with an accuracy that rivals modern engineering textbooks. Hit like if this Roman engineering blew your mind, and let me know in the comments, where are you tuning in from? And honestly, when you see a modern crane now, will you think about those Roman engineers who figured this out 2,000 years ago? I love knowing who's out there questioning how much we've really advanced. Mastering nature's power. From machines that multiplied human force, we moved to those that commanded the elements themselves. The Archimedes screw, invented over 2,200 years ago, achieved something that seemed impossible, making water flow uphill against its very nature. This wasn't just about moving clean water. The screw could handle mud, sand, even small stones. It was robust enough to drain entire swamps or irrigate the hanging gardens of Babylon, one of the 7 wonders of the ancient world. The mechanism is brilliantly simple. A helical screw inside an inclined tube captures small portions of water with each turn, gradually pushing them upward. The optimal angle, discovered through centuries of refinement, sits between 30 and 40 degrees. At about 30% energy efficiency, it might not seem impressive by modern standards, but consider this, it's worked continuously for millennia without complex maintenance. No moving parts to break, no seals to replace, no electronics to fail. But here's where the story gets truly fascinating. Ancient engineers didn't just stumble onto this design, they refined it through systematic experimentation. Different civilizations developed variations. The Egyptians used bronze screws for precision work, while the Romans scaled them up for massive drainage projects. Archaeological evidence from Pompeii shows standardized screw designs, suggesting they had established engineering specifications long before modern manufacturing. Here's the twist. Archimedes never imagined. Today we've reversed his invention. Modern hydroelectric plants use giant Archimedes screws where water flows down through the spiral, turning turbines that generate clean electricity. It's particularly effective for low-head installations under 6 meters. Better yet, it's fish-friendly. Aquatic life passes through unharmed, something conventional turbines can't achieve. In a world desperate for sustainable energy, this 2,200-year-old design is experiencing a renaissance. Building for eternity. While we're examining Roman engineering genius, here's a secret that puts our modern construction to shame. Roman concrete structures from 2,000 years ago still defy earthquakes and ocean waves. While our modern buildings crumble within decades, the Romans discovered something we're only now beginning to understand. They created self-healing concrete. Their secret ingredient was volcanic ash from Mount Vesuvius, which created a chemical reaction that literally repairs cracks as they form. When seawater enters a crack, it reacts with the volcanic minerals to grow new crystals that seal the damage. This is nanotechnology that occurs naturally. Recent analysis shows that Roman concrete gets stronger over time, not weaker. The lime clasts they mixed in act as microscopic reservoirs of healing agents, activated by water infiltration. It's sustainable engineering at its finest, using local materials to create structures that improve with age. But the Romans didn't stop there. They developed different concrete formulations for different purposes. Lighter pumice-based concrete for dome construction, denser volcanic concrete for underwater foundations, and ultra-strong basalt concrete for military fortifications. Each formula was precisely calibrated for its intended use, showing a level of materials science that we're still trying to fully understand. Compare this to modern Portland cement, which begins deteriorating immediately and requires constant maintenance. The Romans built for eternity. We build for profit margins and planned obsolescence. In our climate crisis, where construction accounts for nearly 40% of global carbon emissions, Roman concrete offers a roadmap to sustainable building that actually improves over time. The power of perfect friction. For centuries, the image of pyramid construction has been dominated by one thing: brute force. But that picture is incomplete. The real secret wasn't just the number of men on the ropes. It was a subtle, almost invisible mastery of physics that slashed the energy needed for the job. The tool was the sledge, but the secret was water. A famous painting from the tomb of Jehuti-Hotep, around 1900 BC, clearly shows a man on the front of a sledge pouring liquid onto the sand in its path. For years, this was thought to be purely ceremonial, but in 2014, physicists at the University of Amsterdam tested it. The science behind this is fascinating. By adding just the right amount of water to sand, the sliding friction is reduced by up to 50%. The water forms tiny capillary bridges between the sand grains, making them stick together and creating a firm, smooth surface for the sledge to glide over. It's the same reason you can build a solid sandcastle with damp sand, but not with dry sand. This wasn't an accident. It was precision engineering. Too little water and nothing happens. Too much, and you create a slurry that makes things worse. The Egyptians found the sweet spot through systematic experimentation. They weren't just mindlessly pulling. They were actively engineering the ground beneath them, turning their greatest obstacle, the sand, into their greatest ally. Recent archaeological evidence suggests they went even further. Traces of animal fat have been found on some sledge runners, indicating they combined water-sand preparation with primitive lubrication. They also developed specialized wooden runners with specific curvatures that distributed weight more effectively. This was comprehensive transport engineering, not brute force dragging. The Baghdad batter. We arrive at our most intriguing mystery, a device that fits in your palm but could rewrite our timeline of technological development. In 1938, archaeologists discovered a small clay jar near Baghdad, Iraq. Inside was a copper cylinder containing an iron rod dating to the Parthian period between 250 BC and 224 AD. Its purpose remains one of archaeology's greatest puzzles. But examine its components, and one possibility emerges: fill the jar with acidic liquid, vinegar, citrus juice, or fermented beverages, and it becomes a galvanic cell, producing measurable electric current. If this interpretation is correct, our ancestors discovered electrical principles over 1,800 years before Alessandro Volta's famous experiments. But what would they use electricity for? The most plausible theory involves electroplating, using the current to deposit thin layers of gold or silver onto objects, creating durable, beautiful finishes that would have seemed magical to ancient observers. Recent experiments have shown that arrays of these devices could generate enough current for practical electroplating. Archaeologists have found Parthian jewelry with incredibly thin, uniform gold plating that would be difficult to achieve through conventional ancient techniques, but perfectly matches electroplated finishes. Others propose medical applications, early experiments in electrical stimulation for pain relief, similar to modern TENS units. Ancient texts do describe various forms of electrical therapy using divine sparks and healing lightning, though these could be metaphorical rather than literal descriptions. Some suggest religious uses, where mild electrical sensations might have been interpreted as divine touch during ceremonies. The Parthians were sophisticated in their religious practices, and the ability to create divine lightning on command would have been powerful proof of priestly authority. But here's what makes this mystery truly compelling. It's not an isolated find. Similar objects have been discovered throughout the ancient Middle East, suggesting this wasn't a unique experiment, but part of a broader technological tradition that has been completely lost to history. Skeptics argue the device was simply a storage vessel for scrolls, and its resemblance to a battery is pure coincidence. They point out that if the ancients had electricity, we should find evidence of its use elsewhere: electrical systems, lighting, powered machinery. But this assumes that ancient electrical technology would resemble our own. Perhaps they discovered limited electrical phenomena and used them for specific purposes we haven't considered. Perhaps the knowledge was restricted to particular craftsmen or religious orders and died with them. Without written instructions or definitive context, we can't be certain of its true purpose. But this small jar represents something profound, proof that what we think we know about the past is constantly being challenged. It reminds us that innovation and curiosity are timeless human traits, and that our ancestors may have been exploring realms of knowledge we've forgotten entirely. From the mechanical genius of Roman engineers to the fascinating mystery of the Baghdad battery, one truth emerges clearly: the story of human achievement is far from settled. The conventional narrative of gradual linear progress doesn't always align with the evidence our ancestors left behind. These technologies and mysteries challenge us to see the past not as a closed book, but as an ongoing investigation. They bridge ancient wisdom with modern curiosity, proving that true ingenuity transcends any single era. They remind us that when our complex systems fail, the fundamental principles these ancients mastered — mechanical advantage, sustainable materials, and deep understanding of natural forces — remain as relevant as ever. Perhaps the greatest secret of all is this: human creativity and problem-solving ability have always been limitless. What we call primitive may simply be elegant. What we consider impossible may just be forgotten. And in our rush toward an uncertain technological future, the tested solutions of the past might hold keys to resilience we desperately need. The next time your power goes out, or your complex gadgets fail, remember the Romans with their eternal concrete, the Egyptians with their frictionless sledges, and the countless unnamed innovators who solved impossible problems with nothing but observation, experimentation, and an unshakable belief that every challenge has a solution. Their legacy isn't just in the monuments they built, but in the reminder that true technology doesn't depend on electricity, rare materials, or global supply chains. It depends on understanding the fundamental forces around us and having the ingenuity to work with them rather than against them. 9 technologies. 9 times where ancient and primitive meant something completely different than we thought. But here's the question I keep coming back to. If Roman concrete gets stronger while ours crumbles, if Persian buildings stayed cool without electricity while ours consume it constantly, if one ancient worker could do the work of 60 modern ones, pauser, what else are we wrong about? What other outdated solutions are actually superior to what we use today? Drop a comment. Which one of these technologies shocked you most? Which one made you rethink what progress actually means? And if you want more deep dives into lost knowledge that makes modern tech look, well, maybe not so advanced after all, hit that subscribe button